Alright, so I looked up what in my experience appears to be a famous um, mathematical proof that 1 plus 1 equals 2. So I finally looked this thing up yesterday, the other day, something like that. And actually looked at it, and it doesn't actually claim to be a proof of that at all, which I find amazing because my entire, at least since middle school, I have been told that there is a proof that 1 plus 1 equals 2 that was written in the early 1900s, and it took several hundred pages for this proof to come about. Well, it appears on page 362 of a work, the first volume of a work by Whitehead and Russell, Bertrand Russell, the person that I'm not impressed with him. I think he was a man of pretty average intellect, and but he didn't understand that, and a lot of the people around him did not understand that, so he was blown far out of proportion. That Russell. So what this actually claims, when you look at it, it says, it's got some logical notation and whatever, and we don't even have to get into that to show that this is not what this proves, because there's a comment right below it that says, from this proposition it will follow, when arithmetical addition has been defined, that 1 plus 1 equals 2. That's what it says. So this thing that is shown on page 362 of the first volume of this work is not a proof that 1 plus 1 is 2, because there is a large component completely missing, and that is that it has not yet included a definition for arithmetical addition. Now, it is notable, I think, at this point, that this is necessarily wrong. It's not possible that a proper definition of arithmetical addition is going to yield 1 plus 1 being 2 in all cases, because we can use arithmetic to show that this is not true, right? So if I take, for instance, 1/2 plus 1/3, we get 5/6. So we just got 1 plus 1 is 5, right? Now you're going to object that 1/2 is a number and 1/3 is a number and 5/6 is a number, and so I didn't add 1 and 1 and I didn't get 5. But note what a fraction is. The top part of the fraction is the numerator. That means the number of things we have. The bottom part of the fraction is the denominator. That means the denomination, or the kind, or the unit of thing that we have. So when I have 1/2, what I have literally is, there's a thing and I took half of it. So this is the 1 that I have, that half. And when I add a third, what I'm doing is I am taking this. I'm taking this 1. And then what happens over here is, when I do a unit conversion so that I can actually put these together, because we can only add like units, what happens is I end up with 5 of these things. So 1 plus 1 gives me 5. And we use arithmetic to show this, right? So the half is a unit, the third is a unit, the sixth is a unit. So I am adding 1 and 1 and getting 5 via arithmetic addition. So it's not possible for us to define arithmetical addition in a way that will always give us 1 plus 1 being 2. So, 1, this proof does not claim to prove that 1 plus 1 is 2 in the first place, because it says, from this proposition, it will follow that 1 plus 1 is 2. Secondly, it's wrong, because the missing component, they're just assuming will work, but it doesn't. It doesn't. Right? Now, I think pretty much what's going on here is that Whitehead and Russell are assuming that their variables can represent numbers. And I think this is the problem. This is the real problem, because what we're dealing with here is we're dealing with set theory. We're dealing with, like a formal logic that's handling sets. But numbers are not sets. Vectors are sets. A vector has a unit, which can be anything, and a quantity, which can be any number. But, right, if you have a number of something, that is not the number, right? So I think they're assuming that numbers are what people naively assume they are, but this unquestioned axiom cannot be true. It's not possible. For instance, if we want to say that 7 is a number, but 7 dogs is not a number, then we need to recognize that we made this distinction, right? 7 dogs is different from 7. The power of 7 as a number is that it is unit agnostic. It does not have a unit attached to it. 7 dogs and 7 ounces of soda are both instances of 7, despite the units being absolutely incommensurate. And up to this point, I think this is very intuitive. We understand this generally. But what happens when we introduce arithmetic? Well, positive 7 is really just like 7 dogs, right? It has a unit attached to it, positive. Negative 7 has the same problem. It has a unit attached to it, the negative, right? So what happens when you do addition or subtraction is that you're actually just working with an unsorted list of these things until you find what they reduce to, right? So, something like 7 minus 7, what this really is, it's an unsorted list of positive 7 and negative 7 smushed together, okay? These have direction, and the direction are opposite of each other. So when we smush them together, we get nothing, right? We get 0. No distance occurred, right? So that's why this works. And this also gives us other properties, like we can change this, the order of this, right? So negative 7 plus 7. And note here that here the positive appeared, but here we ignored it. This is going to come up, this is a problem, right? Because we represent this vector as a number casually, but that's wrong. That's a mistake, okay? So yeah, we're working with this. But since they have units, and the units point in opposite directions, these are definitely vectors, right? Right? Because they cancel each other out. The number component is the same, which is why you end up not doing anything. But the direction is different, which is why you end up not doing anything. Right? They're vectors. These are, negative 7 is not a number, it's a vector. Positive 7 is not a number, it's a vector. Right? And then we can easily extend this to the imaginary numbers, right? And this holds up so strongly that we tend to refer to complex numbers as vectors anyway. It's like, why are we saying they're numbers when they're vectors? But now if we think about it just a little bit deeper, if you have 7 dogs, that means you can plot 7 on the dog axis, right? We can make an imaginary axis here, right? And this represents dogs. And we can say, okay, this is 7 dogs. So it's a vector. When we have 7 dogs, that's a vector. It's not different than negative 7 or positive 7, right? So If 7 dogs is not a number, neither is positive 7. If 7 dogs is not a number, neither is negative 7. These are vectors. Now, this all becomes relevant for the proof here, right? Because what we've just shown is that arithmetic does not operate over numbers. It operates over vectors. Because in order to do arithmetic at all, we have to have the sign. And the sign is a unit, and that makes it a vector, right? Because if we have a number and a unit, we have a vector. It's not a number anymore. It's a vector. So 1 plus 1 equals 2 cannot be true universally because we're now working with vectors, not numbers. So the claim that 1 plus 1, the numbers, gives us 2, the number, is not possible. So what happens if your vector units are not commensurate? Well, then you need to apply unit conversions like here, right? So that's where this comes in, right? So we showed here that using arithmetic, we're going to get unit conversions because in order to add two things together, in order to get your unsorted list of stuff to actually bring you somewhere, to resolve to something, to reduce to something, the units end up having to be commensurate, right? So we have to perform unit conversions. I have one of this unit and one of this unit, and when I smash them together, I get 5 of this other unit here. And we can manipulate this so it does anything we want. We can get 1 plus 1 giving us absolutely anything because these are vectors, not numbers. And then there are other consequences, like the fact, as I just noted a moment ago, that integers are not numbers, right? Because they have the sign, which is a unit, so they're vectors. And fractions, well, as we noted, are not numbers because the denominator is the unit, so it is a number and a unit, so it is a vector naturally. So fractions are not numbers, integers are not numbers, but also things like pi is not a number, and I think I casually mentioned this previously, but so what's happening with pi? So let's take a rough circle here. What we're doing to get pi is we're comparing the width of the circle to the distance around the circle. Well, these are two completely different things. What we're doing in order to even make this comparison is we are doing a conversion, a unit conversion at an early level. We're taking that distance around there and we're converting it into a straight line. And then we are comparing it to the smaller line that is this, right? So we're having to do a conversion from this to this, and then a comparison between this and this. So we end up with pi of these little dudes divided by these dudes that have been converted into a longer, a straight line. So there's a lot going on here, right? Pi is not a number because we have all of this unit bullshit happening in order to get it to even make any goddamn sense. In order to ever arrive at it, we have to do a whole lot of work with units. So pi is a vector naturally. In order to get pi to make any sense, it must be a vector. And square root of 2 is kind of the same thing, right? So we take, so there's 1, there's your square root of 2. There you go. So what we're doing is we're taking this diagonal line, we're converting it into a flat line, so very small conversion, and then we're taking, either our horizontal or our vertical, and we are comparing it to this, and we're comparing that length specifically. So square root of 2, here is the little line divided by the big line. So there's units here, right? There's units happening. Now, there's other ways you can get to square root of 2, there's other ways you can get to pi, but it's always going to involve some unit manipulation. There's always a unit involved. So these are vectors, not numbers. And really, like, when you look at this, the logic is exceptionally elementary. Like, literally all we did is recognize that the number component of something like 7 dogs compared to 7 ounces of soda is separate from the unit, right? So 7 is the number, but the unit is what makes us able to, like, manipulate it and play with it and do things with it, right? If we don't have the unit, then this distance around the circle is just 1, and this is also just 1, and they're just different kinds of 1, like this. We have to do a unit conversion to get them to talk to each other, and that's what gives us arithmetic. That's what makes that possible, is manipulating the units, or even having units in the first place. Bare numbers cannot do this. You cannot add 1 and 1. You have to add 1 something to 1 something. And if the something is the same, then you will get 2 somethings. That's true. But there's so much else here, and it's built into arithmetic, that the claim that 1 plus 1 equals 2 has been proven is complete bullshit. And the logic is simple, right? Because we've demonstrated that if we're going to say that 7 dogs, that 7 is the same as 7 ounces of soda, or 7 miles from my house, or whatever, then we have to throw away the unit. The number is separate from that whole thing, and that whole thing is a vector, right? So numbers and vectors are distinct from each other. We have to be able to say this. So yeah, it's disappointing that Whitehead and Russell didn't notice this, but it's Bertrand Russell, so it's not surprising, right?